Good morning. So, yeah. Well, so let's see, a couple announcements for today. Quiz 8 opens up today in about 30 minutes and closes tomorrow at 9 a.m. Covers lessons 21, 22. Quiz 9 is going to be this Friday on the 30th and closes the following Saturday, so Halloween. Covers lessons 23 and 24. So, that out of the way. Any questions on anything? Any homework questions you want me to attend to? Anything crazy like that? Alright, well, time to start some optimization, shall we? Let's do that. So, today is the first of 3 lessons, so we're going to be spending the entirety of this week on optimization. So the idea behind optimization is set up a function that we eventually need to find the maximum / minimum of. So basically with the process of optimization, it's going to be like related rates in that we need to follow a specific procedure, but the procedure is different. So let's take a look at each of these to see what's happening. So what we're going to do to sort of illustrate these 6 steps is we're going to go through a quick example first. So with example 1, here's the premise. So let's get to example 1 right quick, and then we'll sort of go through each of these steps one by one. So the premise is that you have a piece of cardboard that is 6 inches by 11 inches. A square is to be cut from each corner, and the sides folded up to make an open top box. And the problem asks, what is the maximum possible volume of this box? So we have to round our answer to 4 decimal places. So the thing is that with optimization, the first of 6 steps is the following. So while not explicitly required, you really need it. It's really strongly recommended that you draw a picture here, because that way it'll help you visualize what you're supposed to be working with. So with part A, so the idea is that we have this piece of cardboard that's 6 inches by 11 inches. So here's our piece of cardboard. So it's going to be 6 inches by 11 inches. Okay. And so what it's asking us is saying, okay, a square is to be cut from each corner and the sides folded up to make an open top box. So basically what's happening is that if we take a square from each side, from each corner, and each of these are all going to have a side length which we're going to denote x. So x here, x here, x here, and x here. Okay? So what happens from this is that we say, all right, well, that means what we're going to do with this is that we're going to create a box from this. So what happens is that essentially we're going to end up with, once we cut these corners off and then fold the sides from this that are over here, and the 4 vertices here. So once we create a box from folding these sides up, essentially we're going to get an open top box that looks something like this. So what happens is that if we say, let's go ahead and shade this base part here in blue, then essentially what this means is that ultimately, let me draw this in blue and color code this so that we kind of see what's happening. So ultimately what's happening is that if we fold up the sides here, then essentially our open top box is going to look something like this. So fold up these sides, we end up with doop, 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 and doop. And then that's going to give us our open top box as such. Okay? So let's take a look at what this means. So from here, what we have is the following. So what you notice is that, all right, well, if this whole side length here is 6, and these 2 side lengths here are x, then what does that tell you about the length of this side here?
6 minus 4.
Yep, it's just 6 minus, what was it?
2x.
Yep, 2x, right? Because you're taking 6 and you're subtracting two quantities with value x in them. Okay? And then similarly, what would the side length of this guy be? Someone else?
11 minus 2x.
11 minus 2x. Good. So what that tells us is that ultimately, so this side here is going to be 6 minus 2x. This side is going to be 11 minus 2x. And then this side is going to be x. So essentially, our open top box has dimensions 6 minus 2x by 11 minus 2x by x. Okay? So that's all I wanted to say regarding drawing the picture. So now let's move on to step B. So the thing is that we need to identify the quantity that we need to optimize here and what we can control / change. So part B says, all right, well, the problem asks us to find the maximum possible volume of the box. So that should pretty quickly tell you that the thing we're trying to optimize is the volume of this open top box. So goal, maximize volume. Okay? So regarding that, we say, all right, that's good, but what can we control / change from this? So in this case, given this picture here, what's the only thing we can really control here? So if we take a look at this, we say, all right, well, it seems like the best thing we can do is just sort of dictate what each side length here is going to be. So best thing we can do is say, can control length of x. So in terms of that, that's the best we can do. So moving on, part C says, all right, now we need to identify our constraints. So the thing is that regarding this, so the only thing we can really do is say, all right, in terms of our constraints, it seems like we take a look at our dimensions here. Well, it seems like the only thing we can do with this is make sure that each of these dimensions are not negative, right? Because if they're negative, then the problem does not make sense. So what that tells us is that each dimension must be greater than or equal to 0. Or better yet, it must be strictly greater than 0, because if any of these dimensions were exactly 0, then we have 0 volume. So that doesn't make sense. So in this case, we get, all right, so we get that the x's has to be greater than 0. Okay, done deal. But then that also tells us that, so one thing to note here is that with x greater than 0, so one remark, what we control in optimization, usually satisfies this. Okay? But we also have that these two dimensions need to be positive as well, right? So we also have 6 minus 2x has to be greater than 0, and so does 11 minus 2x. Okay? So taking that into account, we say, all right, well, if we solve for x with this inequality here, then what does that tell us about what x satisfies with this part of with this dimension here?
X is less than 3.
Yep, x has to be less than 3, right? And then similarly with this one, that should tell us that x also has to be less than 11 halves. So what this tells us is that this means that because each dimension has to be positive, that tells us, all right, x has to be greater than 0, and x has to be less than 3, and x has to be less than 11 halves. So focusing on these two, we say these both must hold. Okay? So at the same time. So what that tells us is that if we say, all right, well, let's say x equal to 4, right? Well, clearly it would clearly satisfy this inequality here, but it does not satisfy this inequality here. So what that tells us is that we need to be a bit careful with our domain. So we have to make sure that in order for these both to be satisfied at the same time, we have to make sure that x has to be less than, in this case, 3, because if we pick something in between 3 and 11 halves, it only satisfies one of these inequalities, but not the other. So in this case, we need x to be less than 3 here. So constraints are 0, less than x, less than 3. So that means x has to be in between 0 and 3 is our restrictions here. Okay? So that's part C. So moving on to step D. So we have to use our constraints to set up an objective function for the quantity we want to optimize in terms of one variable. So for part D, remember, we need to maximize volume. So in this case, we need to express volume V, express volume V in terms of one variable. Okay, well, so the thing is that, well, the only variable we have here is x, so that should pretty quickly tell you. We need to express V in terms of x. So, given our dimensions here, how can we express volume in terms of x? Yeah, just multiply each of these together, right? So essentially we're going to end up with 6 times 6 minus 2x times 11 minus 2x. Okay? So what we're going to do is we're going to expand this out because essentially because we need to do optimization and find min and maxes, we got to find the derivative of this. So it might help to expand this out a bit to make things a bit easier on our end. So taking that into account, what if we expand this out using FOIL for the last two factors here? What are we going to end up with as our resulting quadratic?
Minus 34x plus 4x squared.
Yeah, minus 34x plus x, 4x squared. Good. 4x squared. So then if we distribute this x into each of these terms, well, that should pretty quickly tell us that our volume is ultimately going to be v of x, which is, if we distribute this x, we have 4x cubed minus 34x squared plus 66x. Okay? So that means that gives us our volume in terms of one variable with this. So in this point, step D is done. Okay? So now, step E says, all right, we have to take our objective function, which is this, set it equal to 0, and solve. Okay? So step E, take the derivative of the volume with respect to x. So then a quick application of power rule should then tell you that their derivative is what?
Well, that's squared minus 68x plus 66.
Yep. X plus 66. Well, just 66, right?
Yep.
Yeah, okay. Okay. So now, it looks like we have a quadratic here. So in this case, let's see if we can factor out any common terms to make our lives a bit easier here. So, in this case, if we take a look at each of these constant coefficients, then what does it look like they all have in common? We just take a look at them. So one thing you should probably be able to see pretty quickly is that these all have a factor of, they're all even, right? So you can pretty quickly factor out 2 out of this. So you should be able to see, well, 6x squared minus 34x plus 33. Okay? So looking at this from here, we say, all right, well, that's sort of the best we can do in terms of constant coefficients. So let's go ahead and set this equal to 0 and solve. Okay? So in this case, we say, all right, well, bless you. In this case, the factorization of this quadratic is not immediately obvious, so it seems like our next best bet is to do what? Quadratic formula, right, good. So, anyone remember a good old quadratic formula / its song? Bingo. So, let me see if I can use a song with these coefficients. So, x equals 34 plus or minus the square root of 34 squared minus 4 times 6 times 33, all over 2 times 6. That was terrible, but I'll take it. Anyways, so essentially here's what we have. So we have 34 plus or minus the square root of all this. So 34 squared minus 4 times 6 times 33. So if you plug this into a calculator, well, this is just going to end up being 364. And then all over, of course, 12. So what this tells us is that you should end up with 2, just ordinarily you would just have two roots from this, right? You would have 34 plus square root of 364 over 12. And you would have 34 minus 364 over 12. But here's the kicker. What happened? Let's go ahead and plug both of these into our calculator and see what happens. So if we plug in, so let's see, let's have someone plug in this root and then someone else plug in this root and see what happens. So what is the, so for those that got the first root approximation, what would that be?
4.4232.
Yep, 4.42. I'll just use those because we'll, 4.4232 you said?
Yeah.
Okay, and then for the other root?
1.2434.
Yep, 1.24, what was it? 34, okay. And for the sake of being a bit more precise, so we're just going to have one more decimal place, then it should be 3. So here's what you notice with this. So if we go back to our domain at step C, what do we notice? Well, remember, our domain needs to be, for all values of x, needs to be in between 0 and 3. Otherwise, any of these dimensions could be negative. Or 0, which doesn't really help us here. So what that tells us is that, oh, wait a minute, well, it can't be this because it's too big. It's outside of our domain. So that means the only value of x we can work with this is this one right here. So that means this is going to be our desired critical point that we need here. Okay? And so one nice thing with optimization is that in usually all but one case, as we'll see on Friday, the nice thing is that you should only end up with one appropriate value for optimization problems. So in this case, you can assume the critical number you get is the critical number you need. You don't necessarily need to check first/second derivative test to see if it yields a min or max. So as a result, in this case, that means we can plug in this value here into our volume function. So if we plug in v of 1.24343 into our volume function, I'll save you guys a bit of time and say that the approximation with respect to 4 decimal places as per the problem statement. So if we approximate this to 4 decimal places, then the number you should end up with is 37.1883. And then this is in cubic inches, because of the fact that the problem says that we are working in inches here. Okay? Now, the thing is that even though this is the desired one, what the thing to notice here is that this actually does give you the absolute maximum based off of our domain, because, so yields absolute maximum, since if we look at v of 0 and v of 3 here, if we take a look at these two values here, well, v of 0, well, that's pretty easily what? Just big fat 0, right? And then what about v of 3? So if we take a look at this factored form, if we plug in v of 3 here, let x equal 3 and say this term here, what happens?
0 again?
Yeah, big fat 0 again. So that means that at the boundary points at x equals 0 and 3, we get 0. So that means our only thing we have to do now is just check the critical point that we got, which ends up being this. So, yeah. So that's example 1. So any questions on any of that before we move on? Okay. So, let's move on to example 2, which is a bit similar. So first off, does anyone still need any of this? Okay. So let's move on to step 2, or example 2. So this one's going to be a bit similar. We're still working with a rectangular object, but what we're going to be doing with it is a bit different. So you're designing a poster with an area of 625 square centimeters to obtain a printing area in the middle and have margins of 4 centimeters at the top and bottom and 7 centimeters on each side. Find the largest possible printing area, rounded to 4 decimal places. Okay. So, again, let's do our six-step procedure here. So the first thing we got to do is, well, we got to draw a picture. So step A is draw a picture. So the problem states that we have to design a poster, so we can assume it to be rectangular. So the thing is that we don't have the dimensions of this given to us, but what we do have is that we have to obtain the printing area in the middle, and the margins on the top and bottom have to be 4 centimeters. So what that means is this. So if we have these two margins at the top and bottom, these have to be 4 centimeters. Okay? And then on each side, we have to have a margin of 7 centimeters. So that means here we're going to have our dimensions be this, so 7 centimeters and 7 centimeters. Okay? Alright. So what this says is that this printing area in the middle is what we need to focus on here. So what this tells us is the following. So if we let this whole side here, denote this by L, and then denote the length of this side here by W for width. Okay? So here's what this tells us. So if we have that, that means that the length of this side here with respect to these margins will end up being what? L minus 8? 14. So we have L minus 14 on this side, and then this side here is going to have side length of what?
W minus 8.
Yeah, that's where the 8 comes from. Good. So W minus 8. Okay? So in this case, this middle part here ultimately corresponds to our printed area here. Right? So the thing is, the problem states that we need to find the largest possible printing area. Okay? So because of that, that says, all right, part B, it says maximize printing area. Okay? So if we denote the area of this printed part by A, then what you should notice is that the area of this should just be the product of the dimensions as per similar to last time, right? So in this case, what we're trying to maximize is W minus 8 and L minus 14. Okay. So I'm going to denote this by asterisk. Okay. All right. Okay. So that tells us that. So in this case, what this tells us is that the things we can control / change, well, in this case, the only things we can really have any control over are the dimensions of the original poster, of the whole poster. So in this case, the only thing we can control is the length and width, which, again, because we're working with area and length and width, we have to make sure these are all non-negative. Okay? Or better yet, because we don't want a zero area, we have to make sure that these are strictly greater than 0 again, because we don't want 0 area. So for part C, so what's our constraint here? All right. So the problem states that we have to design this poster with an area of 625 square centimeters. So what that tells us is that this entire poster here has to have area of 625 square centimeters. So what that tells us is that 625 is the area of the whole poster. So in terms of the variables we already have established, that tells us 625 equals what?
L times W.
Yep, L times W, right? So now the good news with this is that that tells us, all right, now we have a pretty nice relationship between L and W here, right? So what we can do with this is say, all right, well, that allows us to fairly nicely solve for one variable in terms of the other. So what we're going to do is just, for the sake of picking one, what we're going to do is we're going to solve for one of the variables in terms of the other. And for the sake of picking one, I'm just going to express W here in terms of L. So if we divide L to the other side here, what this tells us is that W is equal to 625 over L. Okay? So the nice thing with this is that, like I said, you could technically do the other way around with, L equals 625 over W. And you still have the same final answer, but like I said, I'm just picking one just so we can move on with the problem. So can also use L equals 625 over W will have same final answer. Okay? Okay. Okay. So now part D says, okay, now we have to use our constraints to set up an objective function for the quantity we want to optimize in terms of one variable. So we have that the area A is this, right? That's the thing we're trying to optimize here, right? But this constraint here, what this allows us to do is say, all right, now I can express one variable in terms of the other. So constraint lets us express asterisk above this equation here in terms of L. So what I mean by that is the following. So A here equals, well, W equals 625 over L. So we can say, all right, we can replace W here with this. So ultimately we have 625 over L minus 8, and then we have L minus 14. Okay? So, oh, yep. Let's see. Yeah, there we go. Okay. So, if we go ahead and expand this out using FOIL, what should we end up with as our expression from this?
I got 625 minus 8,750 over L minus 8L plus 112.
Yep. Okay. So if we FOIL this out, we have 625 minus 8,750 over L minus 8L and then plus 112. So if we simplify this down a bit by adding the two constant terms together, we ultimately have 737 minus 8L minus 8,750 over L. So what that tells us is that our printed area can now be expressed in terms of the variable L. So ultimately we have this. Okay? Okay, so now that we have that, let's go ahead and move on to step E, which basically says, okay, now that we have this objective function here, let's go ahead and differentiate it, set it equal to 0, and solve. Okay, so with part E, taking the derivative of A with respect to L will yield us what?
Over L squared minus 8.
Yep, L squared minus 8. Okay, so now that we have that, we say, all right, well, set it equal to 0 and then solve for L here, right? So what we notice from this is that, well, since we're ultimately asked to solve for L, let's solve for L squared first and then we can work from that. So if we have L squared, if we solve for that, doing a quick bit of algebra should then tell you that our L squared x value equals what?
Is it 8 divided by 8, 7, 7,000?
I think you have to mix up a bit. Because remember, we have to add 8 over to the other side. So since L squared is down at the bottom.
Oh, so 8, 7.
Yep.
8,750 over 8.
Right. So 8,750 over 8. So in this case, we say, all right, well, because we're working with the length of a side of a rectangle, we have to make sure that L is now equal to the positive square root of 8,750 over 8. Okay? So, what that tells us is that if we plug this into a calculator, we end up with 33.07189. Okay? So, that tells us that part. So now what that says is that, alright, now the last thing we have to do from this is say, alright, now that we have the desired critical number, let's go ahead and compute the desired quantity. So usually it's checked, in this case you have to check step B to see what you need here. It's usually not the quantity from step E here. So doing that, we'll say, alright, well, in this case we need to maximize this printing area, which is already expressed in terms of L down here. So if we do that, we say, let's go ahead and take the area of 33.07189. So if we plug this value into our expression for A here, in step D, plugging this into a calculator should net you 207.8497 square centimeters. Okay? So that'll be the largest possible printing area for our printed area here. Okay? Okay, so any questions on that part before we move on? Okay, so one thing I'm going to mention here is that before we move on, so remark, this yields max printed area. So one way you can check this is to say, all right, well, we could check the critical point as well as the endpoints again. But what you can also do is we can also use the second derivative test. So since if we take the second derivative and plug this value into our second derivative, 33.07189. If you plug this into a calculator, you should end up with something that's negative if we take this derivative here, derivative of this guy here, take the second derivative. And then if we apply the second derivative test from that, you should be able to pretty quickly get that this is this will yield the maximum that you want here. Okay? So any questions on that before we move on to our last example that we're going to look at? Okay. So, last example that we're going to focus on for today. And then I'll say, okay, the last example that I have in my packet will be similar, so I'll say check the webpage for the solutions on that. So, premise is that Mario has 7m feet of fencing to make a rectangular fire flower garden alongside the wall of his house, where m is a positive constant, so that the wall of his house bounds one side of the garden. We need to find the largest possible area for the garden in terms of m. Okay? So with A, gotta draw a picture. So what happens is that we have this fence that we want to make alongside the wall of his house, so that the wall of his house bounds one side of the garden. So let's say here's his house, and then ultimately the garden is going to be with three sides here. Okay. So in this case, we're going to again want to express L. We have to express this length here in terms of L, and then this side as length W. Okay. So the idea is that we have this rectangular garden that we want to put alongside the wall of his house. That way, the wall of his house is sort of one side of the garden. Okay. So now, if we take a look at the problem, we got to find the largest possible area for this garden. So part B says we got to maximize the area A. So then in this case, if we if we take a look at the variables that we're given, that should pretty quickly tell you that our desired area can be expressed as what? Yep, just length times width, right? So L times W. Where in this case, again, the length and width have to be positive because otherwise we end up with something that's either 0 or negative, which don't really help us here. So control, we can control L and W, which are both positive. Okay? So part C says, all right, well, what's our constraint here? So the problem states that we have 7m feet of fencing to make a rectangular garden. So we have 7m feet of fencing. So what that tells us is that if we take this side here, and this side here, that means that this corresponds to the total amount of fencing because that's the part of the garden that's not directly adjacent to the house. This all has to add up to 7m here. Okay? So, taking that into account, that should tell you that 7m can be expressed in terms of L and W. How? How can we express them in terms of L and W? Let's give someone else a chance. Yep, just 2L plus W. Okay? So what you notice is that, all right, well, we will again need to express one variable in terms of another here. So what we're going to do to make our lives a bit easier is just solve for W because that's already by itself as one term. So what we're going to do is we're going to subtract 2L over to the other side to get W in terms of M and L. Okay? Now, one thing to keep in mind for this type of problem is that M is said to be a fixed constant. We don't know what it is, but we don't need to know what precisely it is. All we know is it's just some constant. M constant and fixed. Okay? So, just one thing to keep in mind for these types of problems. So, now part D says, all right, let's take this constraint and plug it back into our thing from step 2 so we can get this objective function in terms of one variable. So what this tells us is that we have A is equal to length times width, which is just 7m minus 2L. Okay? So that should pretty quickly tell you that you can express the area in terms of length L as 7mL minus 2L squared. So A of L goes here. Okay. So that'll give you your objective function here. So objective function. Okay. So now part E, we say, all right, well, differentiate this, set it equal to 0, and solve. So if we take the derivative with respect to L of our objective function here, what should we end up with as our derivative? Let's give someone else a chance.
7m minus 4L.
Yep, 7m minus 4L. So, okay, so now that we have our derivative, let's go ahead and set it equal to 0. So in this case, since L is the thing that's the actual variable here that we can control, and M is the constant / fixed value, that should pretty quickly tell us that we have to make sure to solve for L here. So if we do that, that tells us L is equal to what?
7m over 4.
Yep, 7m over 4. Okay. So now we have that says, all right, that will give us the desired critical point that we need here. So if we plug in this back into our objective function in step D, we have a of 7m over 4. So what this tells us is that, all right, well, if I'm going to plug this into this form here, and the reason we're doing that is we can, just so that makes our algebra a little bit easier. So 7m over 4 times 7m minus 2 times 7m over 4. Okay? So this part here, well, that's just 7m over 4. Nothing too crazy with that. But then what is this expression here simplified to inside the parentheses? Yep, 7m over 2, right? Because we have 7m minus, well, this part here becomes 2 times 7m over 4, which is just 7m over 2. So you can after doing a bit more algebra, you should be able to see that this is just 7m over 2 as well. Okay? So then multiplying everything together, you should end up with, as your final answer, well, 49m squared over 8. And that will be your desired final answer in terms of m. Okay? Okay, so, make this more like a 9. There we go, that's better. Alright, well, that's basically all I could really cover for today, because I had one more example, but we only got like 3 minutes, so unless you really want to apply some speedrun strats, I think we'll call it good for today. But like I said, I'll put example 4 up on my webpage, but it's fairly similar to what we've been doing up until this point, so you can probably get an idea of what to do from there. But I'll let you check the notes on my webpage if you are stuck on that. Okay. Otherwise, any other questions, anything? All right. Well, otherwise, I'll see you guys either in office hours tonight or on Wednesday when we continue our adventure into optimization. Yep, see ya.